This is what the voltage at the output looks like. As you can see, it looks pretty clean. Hello everyone. Today we are going to take a look at how to make a buck converter. This is one of the easiest projects that you can build, and it comes in very handy. Buck converter allows you to efficiently step down the voltage from your input voltage. The circuit that we are going to build uses N-channel MOSFET and not P-channel MOSFET. N-channel MOSFETs are more efficient and cheaper than P-channel MOSFETs. We are also going to take a look at how the signals look on the oscilloscope. To make the buck converter work, we are going to switch this MOSFET on and off, and to do that we are going to use this gate driver IC. Now you might ask, why do we need a gate driver IC? When the MOSFET switches from low to high or high to low, there is always some time involved in this process. And to keep that time as low as possible, and to keep the MOSFET switching as efficient as possible, we need a gate driver IC. When the MOSFET first turns on, the current is going to come through here, through this inductor. And the inductor is going to build a magnetic field inside it. When the MOSFET turns off, there's going to be a huge voltage spike here, and it's going to travel through this diode to these bus capacitors. You have to use a Schottky diode or ultra fast rectifier diode. Now you might ask, what value of inductor or output capacitors I can use. I have a general guideline for you here. So if you use larger value for output capacitors, you're going to have mostly pros and only one con, which is bulky and more expensive. And same for the inductor, which is large size and cost. So lower voltage ripple, better load transient response, your circuit is going to be able to supply a higher current if your load requires it, like immediately. Slower dynamic response, I count that as a pro. Reduced EMI, same for the inductor. Lower current ripple, better efficient at light loads. Slow response, again I count that as a pro. Continuous conduction mode, we're gonna see what this is on the oscilloscope, and it's better for stable and efficient operation. So by varying the duty cycle from 0 to 100%, we're gonna change the output voltage here. This is gonna stay fixed as it is connected to the voltage here, V bus, and this is the value which is gonna change, and we're gonna see it on the oscilloscope now. So this is what my setup looks like. You got your ESP32. It varies the duty cycle continuously from 5% to 95%. And your input capacitors. This is just a voltage regulator. It provides 5 volts to ESP32. Your gate driver IC, diode, MOSFET, inductor, output capacitors, 2 indicators. I have also connected my toaster oven in parallel to increase the current consumption. At 5% duty cycle, it consumes less than 30 milliamps. And at 95% duty cycle, it consumes more than 2 amps. I'm using this current transformer which I made myself with the 50 turns of wire and 100 ohms of termination resistance. This is just N87 toroid core. I'm going to show you one extreme example. I'm using 25 kilohertz frequency here. Yellow signal is the gate drive signal, and the pink signal, when I'm going to turn on the power supply, is going to show you the current through the inductor. As you can see here, there is sort of like a knee forming, like here. When you see this means that your inductor is going into saturation. So you should really try to prevent this. To avoid this, we're gonna increase the frequency. Just a moment. As you can see here, I have increased the frequency to 100 kilohertz. I'm going to turn on the power supply now. As you can see, that knee problem or the inductor saturation problem is fixed. But this is what I was talking about earlier, the continuous conduction mode. Here, the current through the inductor is flatlining, and we should really try to avoid this also. To avoid this, I'm gonna increase the frequency even further. 1 second. So I have increased the frequency to 200 kilohertz now, and let's see what it looks like. It looks pretty neat. No knee, no flatlining, and this is what it should really look like. So now we are using 40 microhenries. Let's say if we were using something like 100 microhenries or 500 microhenries of inductor, then we could have even used lower frequency and still not get a flat line. So that's what I was talking about earlier. And this is what the voltage at the output looks like. As you can see, it looks pretty clean. Now we are going to see what your signals will look like if your wires are really long, they are all over the place, and none of them are twisted together with each other. 1 second. So I am supplying 30 volts with my power supply. As you can see here, it's 50 volts per division, and there is a lot of noise on the output whenever the MOSFET turns on or turns off. There is over 50 volts of noise, and that's really bad. So guys, this is it for today's video, and I'll see you next time with further improvements to this circuit.